Hello everyone, and welcome back to AssemBLOCKS. I know it's been a few months since my last update. I believe the last one was in September, but I'm really happy to say that I've had time to work on the game again, as it is second semester of my senior year, and this is one of my independent study projects that I have signed up for. And so therefore, I have time allotted in my day to work on this, and I've been making great progress. So the first thing that you might notice is it doesn't look anything like you remember from any of the previous videos. And that's because I've been rebuilding AssemBLOCKS from the ground up, both in terms of the processor simulation, as well as in terms of how it appears to the user. And one of the main things there is this pass-through mode, which I'm not going to turn on right now because it won't actually show up in this recording. However, I'm able to use both pass-through as well as physical objects in my room as my table that I built the computer on. So if, for example, I click on right here one of these tables in my room, you can see that now I have a solid surface below my hand, but one that I can also put physical objects on. For now, for this video, however, I'm just going to set it to the virtual table, which should be pretty reminiscent of before. And finally, the gaze cursor, if I turn that on, you can actually see that blue dot floating around the scene. And that's where my right eye is pointing right now. So that's going to be useful in the near future when I start to build some of the tutorial parts of this simulation game, because I'll be able to tell where people are looking when I'm talking about different things. Because it's a little distracting, though, I'm going to turn that off for now. So I guess we can now hit continue, and we have nothing here. Where is the computer from before? I've put it into this menu right here, which you can see has a handle that lets me move it around a little bit. And in the menu, there is both a Tools tab as well as a Components tab, and that's where you can find everything that we remember from before. So maybe we should get started by putting together a computer. I like to start with the processor, and you'll notice that whenever you go to create a component, now you just kind of point at the table where you want it to show up, and then when you click once, it becomes one that you're actually able to grab and move around. So I'm just going to stick that right there and make it clock. You can see in this new version that I have not really implemented any of the clock controls, and so it's actually just a ugly menu of options here. But we're able to connect that clock up to the processor, as well as a reset button to the processor. All of that works just the same as before. I've taken the same models, although the connection system has been revamped to be a little bit more robust in figuring out whether things can actually or not, and handling things that are plugged in the wrong place. So I guess I will now connect that processor up to the memory bus, which looks at the beginning pretty similar to before, although you'll notice that all of the components now do have a small label in front of the, or below the icon, telling you exactly what they are. And if I now connect something like the EEPROM up to this memory bus, you'll notice that not only does it change that text right there from disconnected to some sort of connected indicator like before, it actually shows the address that the EEPROM has been mapped into the memory. And that happens automatically, so if we have, like, for example, multiple versatile interface adapters, we're actually able to have the memory bus automatically assign them a position in memory that they can be accessed from. And then you're able to see that position and write your code in order to accommodate that. Next up, I think I will attach a memory monitor to the system, which has not changed significantly from before, other than it does have slightly better indicators of issues. And so that means then that if I grab out these couple of numbers, I'm able to put in replacement numbers that will be able to read from like 8000 to FFFF. But I'm going to wait on that for a minute to demonstrate it all as one. So let's now finish off by making a versatile interface adapter, as well as a port visualizer, and we're just going to go for that same sort of marquee effect on port B that I've been demonstrating for what is almost a year now at this point. So if we connect that up, you can see the versatile interface adapter. It now also has some registers available in memory, address 6000, at least starting there. And if we were to run the program right now, nothing would happen because currently the EEPROM is just filled with EA bytes or no ops. And so nothing's actually going to happen. The processor will just sit there. The clock ticks every half a second when you hit run or manually. And so, in the time that we watch it, it might get through like 20 cycles of no operation. However, at this point, we're able to switch over to the Tools tab, and we see that there's a couple of different options here for us. Maybe I will move this menu off to the side a little bit and create this calculator. You'll notice that the calculator looks pretty similar to the keypad from before. That used to be like over here on the table. And that's because I wanted to keep the exact same functionality with inputting hex, decimal, and binary numbers into the system. But I also wanted to add some like nice programmer's calculator features, like bit shifts, addition, subtraction, multiplication, two's complement arithmetic, as well as a couple of different logical operators here. And so that's how we're going to be able to create numbers to put into the memory monitor. Because you see it says it's missing some start and end addresses, right? So our start address is going to be at 8000 hex. So if we go into hex mode and select a 16-bit word, we're then able to type in hex 8000. We can see in decimal mode that it's 32,768 and create that as a tile. And then it still says it's missing an end address, and we know that this thing is able to display 256 bytes of memory, so we'll go to 80FF. We are in decimal mode here. Let's clear everything out. 80FF, which we can see is just a little bit higher than 8000. Let's go back and create it, put it in there. Whenever we write in our program, then we'll be able to make sure that it actually shows up. So how do we write in that program? Well, that's why we have this machine code editor and instruction set here. So maybe I'll start with the instruction set. You can see that there was like a little bit of a glitch when I pressed that button just because it was a lot for it to spawn in all at once. However, I will put that up here, and in the near future, performance of that system should be greatly improved. So you can see that the instruction set is now just not floating off in space somewhere. It's once again attached to one of these handles with a close button. I can close it, go back to the main menu, and open it right back up. But it also has a slightly improved filter mode that's going to let us write our program more easily. So with the instruction set there, maybe we could get started with just like lighting up all of the bits on this port visualizer right here. So we would definitely need a load a immediate instruction as well as a store a absolute instruction. And then in order to light up all the bits here, that's an 8-bit system, so we're going to select 8-bit word because it takes exactly like 8 bits of data through here onto this port B. And we can set them all to 1 if we want, which manually is a bit of a tedious process, but I guess you could also type in FF in hex, and we can create that tile. You'll notice that if I take my cursor and hover over the tile, it tells us both the decimal conversion as well as the binary conversion of that number. And then we need to store it out at address 6000 right now. So we're going to go into the hex mode, type in 6000, and we need a 16-bit word, so let's clear that out. 6000, there's our tile. Except you might remember that this system actually uses a little endian format for numbering. And so therefore we can't just put in 6000 as a single byte because really this is 2 bytes. It's a 16-bit address. So therefore we actually need to split it up into a couple of 8 bits. So right here we have a 00, which is that least significant portion, as well as a 60 for the more significant half. And that's actually what we're going to put into our code. So where are we going to put that? Well, that's what the machine code editor is here for. And you'll notice that it looks very similar to before, just potentially slightly more polished. You can see we're able to select what the default value to fill all the empty spaces in the EEPROM is, as well as change both the reset and interrupt request vectors. Remember from before that I haven't actually created a port for the non-maskable interrupt, although I have implemented it into the new processor simulation, which should be able to reach even higher speeds than before thanks to a couple of new memory management techniques that I implemented. So we will take our load A, put it in up at the top, as well as our store A. With that done, I guess we can try and write it to the EEPROM now. You'll notice that the EEPROM has the same port as before for its EEPROM programmer. So if we go back to the Components tab and get out an EEPROM programmer, I know that the text is red right now. It's just a warning that some functionality may not be exactly as we expect it. I will put in that EEPROM programmer right there, as well as create a couple of chords. And the first chord is just going to connect the EEPROM to its programmer. And then the second one, however, is kind of new. It will connect a programmer over into our code editor. And so that way we're able to tell it, at least in the near future, once I've implemented assembly programming as well, because that is not in the new simulation yet, it's able to tell it what source we want to take the code from. So you can see it's almost a cascade of data from right here where we write all of it. It puts it together into a 32 kilobyte like binary file essentially, and transfers it to the EEPROM programmer, which then writes it into the EEPROM. And obviously it is then accessible by the processor through the memory bus. So let's click Write to EEPROM, and now maybe put in our end address right here. And with that in, we can see that it's mostly EA bytes because obviously our program was not very long, was it? However, you can see that we have A9FF and then 8D0060, which does directly correspond with what we've typed in here, and that is how the machine code editor works. Everything that you put into all of these boxes is simply directly placed into the EEPROM. Whereas with assembly, it runs through the assembler first, which converts it from the higher level assembly code into this machine code, and then puts it on the EEPROM. So our clock is set to half-second cycles, so if I press reset and then run, we can see that they light up pretty quickly. And now, right now, yes, the clock is running, but, you know, with every half second, it's just going to be moving along through all of these EAs, and we would never see the end of the EEPROM at this rate. However, I guess we can stop the clock, and we'll need to get started on a little bit more code here. So the first thing I'd like to do is replace maybe this loading FF with something else, right? For that marquee effect, we always used 55 hex, and if I change that to binary, you can see why. It is alternating between zeros and ones, with the 1 here in the ones place, and then not all the way over here in that 128 place. So we'll create that 55 number, as well as AA. I need to be in hex mode for that, as well as AA, which if I convert it to binary, you can see that the ones, if I hover over that, are just in the opposite places before. So I will create that tile as well, and then I guess we can put one of them into our program right up here. Then we just need to duplicate these two lines, so let's grab out another couple of A9 commands, and if I set this to load, you can see that it's highlighting all of our load instructions. You might notice something new here. This column didn't previously exist, and that's because most of these opcodes in here are this strange addressing mode that we haven't seen before. And that's actually just a 65C02 addressing mode. Basically, in the newer version of the 6502 that the Western Design Center made, they added a couple of extra opcodes for us to make things easier. You can see if we look around in here, there are definitely a couple of extras that might be even more useful. For example, store 0 in the 0 page. So as opposed to having to load 0 into the A register first and then store it, we could just store that directly if we needed to use it for some sort of index. However, in this case, we're just going to grab out another A9, as well as an 8D for load A and store A, just like before. I dropped that one. Put them into our program, and now we can put, where is it? There's our AA. So 55 here is just the negation of AA. Then obviously we also need to duplicate the 0, 0, and 6, 0, so we will deal with that now. 0, 0, obviously because our input right now is just 0, we can just press enter and it's there. 6, 0, we'll type it in hex mode, and then it is all set. I guess we could now maybe write this to the EEPROM and see what happens. We will stop the processor, reset it, and then run it again. We can see that it changes once, but then it stays stuck on the second one, and that's just because after this, it's just going to be EA bytes once again. So we do need a way to jump back to the beginning of the program. And we've all seen that before. Down here in the control filter, I guess, is our jump instruction with an absolute address that we want to jump to. So we'll put that in, and then we know based on our reset vector that the beginning of our program is 8000, address 8000 in little endian, you can see right there. So we're just going to type in 8000, and put those right into our program. Clock, reset the processor, write our new program out to the EEPROM, and press run. And you can see that our port visualizer is now switching back and forth just like before. So where am I going to go from here? Well, you can see that there's plenty of space in here in this Tools tab for more tools. Obviously, we need to get an assembly editor here, as well as a palette of assembly language instructions, as opposed to just this giant table of opcodes for us. In addition, we definitely have a couple more components that we do need to bring back into the new version, including that monitor over in the corner, the big old CRT monitor. And I want to bring in a couple of new ones, such as a 16:2 LCD display, as well as a couple more inputs. So right now we have like this button. I would love to have some buttons that we can, buttons or switches maybe a set of like 8 dip switches, for example, that we could connect to like port A or port B and then read them. Because I did implement in the versatile interface adapter when I was rewriting that code, the ability to set ports to both input or output. And so with that implemented, then we should have a much improved version of Processor Simulator that also kind of meshes with your real-world environment, which I hope to be able to demonstrate soon, as I can get a recording of my pass-through camera working. In the meantime, however, I think I will be signing off with this update, and I'm hoping to bring you another one within the next month when I have some more huge progress. So thanks so much for watching this video. It's been Sig from PicoPlanet, and I'm hoping to see you again on this channel sometime soon.